alright. Little darling, it's been a long, cold, lonely winter. Little darling, it feels like years since it's been here. Here comes the sun. Here comes the sun. I say it's alright. Hey guys, guess what we're going to talk about today? That's right, the sun. We're going to talk about, go through this lesson, and I'm going to let you highlight or underline some of the important facts. We're going to skip around a little bit. We're not going to cover everything because we're going to just do this in about 1 week. So pay attention, underline in your packet what's underlined on this video, and this will help you with the studying and for your study guide that you have to fill out and for our test that's coming up. So let's get started. The sun, mostly just the properties of the sun. We're going to talk about the structure and the layers of the sun and its atmosphere and just the parts that make up the sun. So let's move on to page 76. Here comes the sun. It says, what do we know about the sun? Since early in human history, people have marveled at the sun. Civilizations have referred to the sun by different names. Gods and goddesses who represent the sun were worshipped in different cultures. In addition, each astronomical observation were established to track the sun's motion across the sky. Let me get my glasses. By the mid-19th century, astronomers have discovered that the sun was actually a hot ball of gas that is composed mostly of the elements hydrogen and helium. And we learned this when we studied the stars, because the sun is a star. It's made up of mostly hydrogen and helium. Scientists now know that the sun was born about 4.6 billion years ago. And to the side, I put this is a theory because we don't know for sure. No one was there. They're just basing this on what they have seen and observed. And as you know, scientists come up with a hypothesis, but until it's proven, it's still a theory. So they're just basing this on what they think, but it's not an actual fact. Every second, 4 million tons of solar matter is converted into energy. Of the light emitted from the sun, 41% is visible light, another 9% is ultraviolet light, and 50% is infrared radiation. And perhaps the most important part of all, without the sun, there would be no life. Down here is just a few of the statistics that we're going to talk about. You may need to answer some questions later on in your study guide about the surface temperature. This is where you would find this information here, and the composition, what makes up the sun. It was listed up here, but it's also in this little chart, along with some other information that you might need. Okay, I have a little video real quick for you to watch.
Pop quiz. What's the closest star to Earth? It's called Sol.
Never heard of it, you say?
Sure you have. Sol is the sun. Ancient Romans, who once worshipped the sun, called it Sol, and it's become the kind of official scientific name for the sun. It's where the term solar system comes from. Sol, or the sun, is the star at the center of our 8-planet solar system that provides us with energy. Without the sun, Earth would be a dark, frozen world with no life. But how does the sun's energy get to us? Well, first, let's talk about what the sun is. It's a 5 billion-year-old big ball of super hot gas. The hottest part of the sun is its core, or center, which is about 15 million degrees Celsius. Whoa. Its surface is not quite as hot, but it's still almost 5,600 degrees Celsius, which is pretty toasty if you ask me. And as for its size, the sun is so huge, you can line up over 100 Earths along the face of it, and more than 1,000,000 Earths could fit inside it. But the sun's size isn't what makes it seem so big and bright to us on Earth. It's because it's so close to us that it seems way, 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 way bigger and brighter than other stars. So, you know that the sun is hot and bright, and that heat and light are both kinds of energy that we get from the sun. Let's take a look at a model to see how the sun's energy gets from good old Sol to our planet. Here's the sun. Energy is created in its super hot 15 million degree core. That energy then travels outward from the core to the surface of the sun. But this journey from the center of the sun to its surface can take over 100,000 years to complete. But once the energy deep inside the sun finally gets to the surface, it travels as light and heat all the way to Earth. In fact, it only takes about 8 minutes for light to travel approximately 150 million kilometers through space to Earth over here. That's not such a long time. So to sum up, energy is created in the sun's core. It travels very slowly to the sun's surface before it takes a super speedy trip to Earth in the form of light and heat. And you and I can see and feel that energy as sunlight. Without the heat and light we get from the sun, Earth would be just a frozen ball floating around in space, which would be a total bummer. So, thanks, Sol. You're a real star.
Alrighty. Okay, so now let's move on to the structure of the sun. You might have, you'll hear some more of this. You heard some of this in the video, so let's just talk a little bit more about this. All right, sorry about that. The composition of the sun and the earth are different. However, two bodies are similar in structure. Okay, what makes them up is different. You know that the sun is made up of hydrogen and helium, which are gases, but the earth, we have it's a rocky, dense terrain, solid. So the composition, what makes them up, is different, composed of, but they do have some similarities. So let's look at those. However, the two bodies are similar in structure. Both are spheres, and both have layered atmospheres and interior composed of layers, which is just saying that, we have an atmosphere, so does the sun. It has layers on the inside, and so does the earth. In the middle of the sun is the core. This is where the energy is produced, and from the core, energy is transported to the sun's surface through the radiative zone and the convection zone. So it starts here in the center and works its way out. The energy is composed in the core. The sun's atmosphere has 3 layers. You've heard about these before when we talked about stars: photosphere, chromosphere, and corona. The sun's surface is the photosphere. Energy escapes the sun from this layer. This is where we see most of the visible light coming out of, and It is the closest part to the sun. The next layer is the middle layer is of the sun's atmosphere is the chromosphere. The temperature of the chromosphere rises with the distance of the photosphere, and the sun's outer atmosphere is the corona. And the corona is Latin for crown. It extends millions of kilometers into space. Millions. So this is a big, well, huge layer. So let's look at this right down here in the diagram. I just kind of sectioned it off. You have 3 atmospheric layers, and then you have 3 sun layers to make up the sun, or zones. So here, this is just where you can find some information for your study guide. You'll need to know these layers, where they are, maybe locate them on the sun. We're going to do a diagram tomorrow on Wednesday, and you're going to draw this out. So this is a great source of information here. So this is the atmospheric layers, the corona and how hot it is, the chromosphere, the middle layer, and then the photosphere, the visible surface of the sun. And this is where the light and energy escapes into space. And I have a video for you for that.
I've been obsessed with belts for a long time. I wear a belt every day, and there was like 3 things that I always show.
The Sun is an extremely complex main sequence type G2V star, whatever that means. Even the most brilliant minds and NASA don't completely understand that, but learning about the Sun's layers and the basics of what they do is pretty simple. Let's start with the outer layers. Did you know that the Sun has an atmosphere like Earth? Pretty cool, huh? The outermost layer of the Sun is called the corona, which is Latin for crown. Surprisingly, this outer layer is one of the hottest at around 2 million degrees Fahrenheit. That's not cool. At these temperatures, atoms like hydrogen are stripped of their electrons, leaving only a bare nucleus. The Sun's magnetic field lines trap hot plasma and form spike-like shapes called streamers. These are what give this layer its crown-like appearance and name. The corona also causes the northern lights here on Earth. As plasma flows out of this layer into space, it eventually hits the Earth atmosphere and interacts with atoms and molecules. And these reactions cause the beautiful colors that we see. The next 3,000 miles is the Sun's chromosphere, which is Greek for color sphere. Now the temperature suddenly drops to around 36,000 degrees Fahrenheit. And at these temperatures, hydrogen atoms begin to radiate in a reddish color, hence the layer's name. But against the brighter background layers, you can only see the chromosphere and the corona with special, expensive equipment. However, once in a while, we get a rare look from Earth at both of these layers during a solar eclipse, like the one in 2017. The moon temporarily blocks the much brighter layers, allowing us to see the corona and the chromosphere. Finally, we reach the photosphere, which is Greek for light sphere. This is the layer of the Sun that we're all most familiar with, because it's where visible light first appears on the Sun. And now temperatures fall to a nice chilly 6,000 to 11,000 degrees Fahrenheit. The photosphere is also where we see sunspots, which are randomly appearing dark spots that are around 3,600 degrees cooler than the rest of the layer. You've probably seen pictures of the photosphere, whether you knew it or not. It's covered in a granular-like pattern, kind of like skin. This pattern is the result of wild convection processes happening in the layers inside the sun. So now you know what the layers of the sun's atmosphere are, and a little bit about how they work. In another video, we'll
Okay. And then the inner part of the sun, the mostly instead of layers, they're called zones. You have your core, of course. The very dense center of the sun, the core has a temperature of 15 million degrees Celsius, which is hot enough to cause the nuclear reaction that produces energy in the sun. Nuclear fusion happens here. And then it moves out as it moves out to the radiative zone. The radiative zone is the layer of the sun through which the energy is transferred away from the core by radiation. And then it gets to the convection zone. And this is a very slow process as it moves out. It takes a long time for it to get out through here. I mean, it's huge area, but it also takes a long time. The convection zone is the layer of the sun through which energy travels by convection from the radiative zone to the photosphere. So it's just, and it cools a little bit, and then it heats up. When it gets closer to here, it heats up, and then as it gets out, it cools, and then it goes back. So it kind of gets stuck in this little loop here for a while, and then finally, eventually, it comes to the surface. So I have a video for that.
Deep inside of the sun is the innermost layer, the core, which is a gigantic nuclear factory 195,000 miles thick. That's the equivalent of driving from New York to Los Angeles 70 times. In this most mysterious layer, the crushing pressure feels 150 times stronger than being deep underwater. Pressure and density are so great in the core that hydrogen atoms smash into each other, combining to form helium. Now atoms become highly unstable and release nuclear energy to become stable once again. We call this process nuclear fusion, and it's the very process that keeps the sun and all stars alive. Every single bit of energy that leaves the sun and reaches Earth originated from the core. The core is the sun's hottest layer. How hot? 27 million degrees Fahrenheit. That's hot enough to instantly melt lead, iron, brass, or any other metal. Just above the core lies the radiative zone. Now, the nuclear energy generated in the sun's core travels through the radiative zone in the form of electromagnetic radiation, better known as light. Density slightly decreases, but is still tremendous. The radiative zone is 186,000 miles across. And ironically, this is how far light can travel in 1 second. However, the radiative zone is still so dense that photons of light bounce around like a pinball machine. In fact, light takes around 100,000 years just to make its way through the radiative zone of the sun. Finally, we reach the convection zone, which spans for around 124,000 miles. Now density finally becomes low enough for light traveling out of the core to transform into heat. And just like this layer's name, the process of convection kicks in. Simply put, convection means hotter materials will rise, cooler materials sink. And as the heat from the bottom of the convection zone rises, it gradually cools, sinking back down again. This continual process happens in gigantic bubbles known as convection cells. Convection is also the same process that causes the big bubbles in a boiling pot of water. Well, there you have it. Now you know a little bit about each of the sun's inner layers.
we're going to skip over the nuclear fusion part. This is kind of what you can read over this if you're more interested in it, but you just need to know the fact that that's where the core is where this takes place. And this is a little bit more about radiation and convection in these zones. You need to know that the energy is transferred to the surface of the sun by two different processes, by radiation and by convection. And energy flow from the sun's core outward to the sun's surface by radiation and convection happens continuously. By radiation is energy travels through the radiative zone in the form of electromagnetic waves. The process in which energy is transferred as electromagnetic waves is called radiation. And then convection, energy that reaches the top of the radiative zone is then transferred into the sun's surface. In the convection zone, energy is transferred by the movement of matter. Hot gases rise to the surface of the sun, cool, and then sink back down to the convection zone. This process in which heat is transferred by the circulation or the movement of matter is called convection. So basically, you just need to know that these are the two ways that they move out of the sun. Kind of like this is where light happens, and this is where heat happens, and it just kind of moves and eventually gets out into the atmosphere. And then the sun does rotate, and we're not going to go into all of that this week. The Ring of Fire, we will talk a little bit about sunspots, solar flares, and prominence. So what you need to know about sunspots. This is what is solar activity? Solar activity refers to variations in the appearance or energy output of the sun. It's just what's going on when you look at the sun is basically what it says. Sunspots are dark areas that form on the surface of the sun called sunspots. Sunspots are places where hot convecting gases are prevented from reaching the sun's surface. Sunspots can appear for a period of a few hours or to a few months. It does talk about the sunspot activity occurs on average in 11-year cycles. I didn't underline that, but that's an interesting fact, and it has to do with the rotation and the way the sun moves. And then solar flares. Solar flares appear as very bright spots on the sun's photosphere. A solar flare is an explosive release of energy that can extend outward as far as the sun's outermost atmosphere. Temperatures within the solar flares reach millions of degrees Celsius. And then prominence really has to do with there are huge loops of radiative cool gases that extend outward from the photosphere thousands of kilometers into the outer atmosphere are called prominence. And so that's basically, we have a little video that kind of explains a little bit about this, but I just wanted you to be aware of those terms, and we're not going to go too deep into that. Let me find that last video.
Kitt Peak Observatory in Arizona. Solar astronomer Matt Penn studies this solar surface to discover how photons of light get trapped.
There's a bunch of theories today, but hopefully we'll get some data.
Using the McNath Pierce telescope, he focuses the sun's light to scan the photosphere in detail.
So what we've got are a few small sunspots on the disk of the sun. We've got two sunspots, two large ones. They're heading off to the edge of the sun, to the limb of the sun. But they're all accompanied by smaller sunspots, groups of smaller ones following them.
Sunspots mark areas where light is trapped.
So a sunspot forms a dark spot by removing energy from that part of the sun. It's blocking the convective flows that transport the heat and the light from inside the sun to space, and so what we see then is a cooler region that appears dark to us.
A powerful force stops our photon dead in its tracks, preventing its light and energy from leaving the sun's surface. That force is magnetism. Sunspots take shape where intense magnetism from deep inside the sun blasts up through the photosphere.
The magnetic fields are so strong that it actually stops the convective motion of hot inner material from flowing to the surface. So you actually get what looks like a cool spot on the surface of the sun.
They can be huge, the largest over 10 times the size of Earth.
All right. Thought I had one more. There it is.
Stay put for world-ending coronal mass ejections, real video of the sun's surface with sound, and incredible images of our sun as you've never seen it before. At the center of our solar system is the one thing that has made life on our world possible: the sun. A blazing ball of plasma radiating heat and light, with structures as large as the state of Texas, propelled by convection currents around its surface, and a mass so large it keeps every object in our solar system spinning around. In today's video, we're going to explore the mysteries of the biggest object in our nearby space and show you the sun as you've never seen it before. We all know that the sun is the most important part of our solar system. Not only do all of the planets orbit it, without the sun, we would not have the light or warmth to sustain life on planet Earth. But while the sun is a good thing for us on Earth, getting much closer would be a pretty bad idea. That's because the sun is in fact a giant sphere of superheated ionized gases. As far as composition goes, the sun is made up of 70% hydrogen, 28% helium, and then a variety of carbon, oxygen, and nitrogen to make up a further 1.5%. Some smaller elements like neon, iron, silicon, magnesium, and sulfur make up the remaining 0.5%. As time passes and the sun continues to burn, those percentages will slowly change. The reason the sun is shining at all is because of the nuclear fusion reaction powering its extremely hot core. This occurs due to how much mass the sun holds. At its core, the force of gravity is so strong that hydrogen atoms are squeezed together until eventually they merge. 4 hydrogen atoms merged together will create 1 helium atom, with some of the hydrogen atom's mass being converted to heat and light as a result. From planet Earth, the sun looks like a rather stable celestial body, but closer inspection reveals that the roiling plasma that makes up the sun is anything but. Solar flares occasionally rip out of the surface of the sun, shooting particles out into space in what is known as coronal mass ejection. These solar flares are thought to be caused by something known as magnetic reconnection. They are a sudden explosion of energy caused by the tangling or crossing of magnetic field lines. Solar flares aren't always strong enough to create a mass coronal ejection of plasma and sometimes just manifest as an area of increased luminescence. But when plasma is kicked out of our star, it can be a breathtaking phenomenon, with the largest flares having the potential to knock out all electronics on Earth. For the most part, these huge solar flares miss Earth, but if one were to hit, it would have catastrophic consequences. But this sort of activity isn't happening all the time. The sun goes through its own solar cycle. Every 11 years, the sun's north and south poles trade places, a cycle which has been observed for centuries by changes in the appearance of the sun itself, as well as phenomena like aurora here on Earth. Over the course of this 11-year cycle, activity on the sun can be observed in a state of synchronized fluctuation. Solar flares, coronal mass ejections, sunspots, coronal loops, and even the level of solar radiation are all tied to these 11-year cycles. The peaks and dips in this cycle are called the solar maxima and solar minima. At the maximum point, sunspot activity will be at its height, and solar flares shooting billion-ton clouds of ionized gas into space are common. On Earth, this means we will see many more aurora as the ejected particles from the sun collide with our atmosphere in a dazzling display. Space agencies, however, have to be on high alert. Radiation storms hurled out by the sun across the wilds of space may be beautiful from the ground, but they can be dangerous to astronauts in orbit. Satellites and other communication systems can also be damaged in this time of solar maxima by rogue storms of solar radiation. Minima are the exact opposite. Sunspot and solar flare activity is almost non-existent. Sometimes days and weeks can go by without any form of major solar activity. Observing the sun from Earth and from satellites in orbit has taught us much about how the sun operates. As you are looking at these images, you may be confused as to why there are so many different colors. If you were to take a photo of the sun with a standard camera, you would get to see a familiar yellow-colored orb. The sun exhibits this color in photography because yellow is the brightest wavelength from the sun, so that is what our eye and basic cameras pick up on. Not that you should be looking at the sun with your eyes directly. The truth of the matter is that the sun emits light in all colors, right across the spectrum. Scientists take images of the sun with specialized instruments both from the ground and from orbit. Some of these instruments go deep into the ultraviolet range of the light spectrum. This is better for looking at phenomena like solar flares, which are mainly unobservable through the naked eye. The Daniel K. Inouye Solar Telescope, based in Hawaii, observes the other end of the spectrum from visible to near infrared. The image you are looking at, taken by this telescope, is the highest resolution image ever taken of the sun. Each of these cell-like structures are around the size of Texas. They are hot, excited, convecting masses of plasma. Let's zoom in to get a clearer view, and for the full effect, we have added the sound of the sun, which was created by observing the vibrations from the sun over 40 days and transformed into audible sound. The sun is both a provider, yet also a destroyer. Venus, the second planet from the sun, is the hottest in our solar system. Heat from the sun is exaggerated by its thick atmosphere and high pressures on the surface. But did you know that we have actually landed on Venus and taken images of the surface? Click here to find out what the Russian probes found when they touched down on Venus. Thanks for watching Elder Fox.
All right. And down here it just talks about the sun's composition, what makes up the layers of the sun. There's 6 layers, 4 for the atmosphere, 3 for the atmosphere, and 3 for the layers in the sun. So you can just write those in. The if you start at the center, at the beginning, the innermost level is the core, and then you have the radiative zone, convection zone, then you have your photosphere, chromosphere, and then corona would be the last one. And then energy is transferred from the sun's core to the photosphere. And what is the process? It starts in the core, nuclear fusion, and then moves to the radiative zone, that's A, and then to B, the convection zone. And that's it.